Alright, on to epoxidations, which is still a lot of syllables. Epoxidation, okay. An epoxide, you guys haven't seen these before. Epoxide is a three-membered cyclic ether, and they're valuable synthetic intermediates because they're often used for converting alkenes to a variety of other functional groups, including alcohols and other ethers. An alkene is converted to an epoxide by use of a peroxy acid. Okay, carboxylic acid that has an extra oxygen atom with a peroxy linkage. We'll see this. The mechanism of epoxidation is concerted with a lot of bonds breaking and forming all in one step. So it's going to take a lot of practice, but I promise you guys will really like this mechanism because it's really fun. Okay, so here's what it looks like. We take an alkene and we throw in our peroxy acid. I'm going to keep it nice and ambiguous with the R group there. But here's our peroxy acid because it's got a peroxy linkage here, this OO linkage, right? That's what can be found in peroxides. Okay, so this is a peroxy acid. And what we get out then is an epoxide. Looks like this. It's a three-membered ring with an oxygen. It's a cyclic ether. Okay, and we also get as a byproduct our carboxylic acid, a carboxylic acid out, derived from the peroxy acid. Okay, so this is an epoxide. Again, it says three-membered ring with an oxygen. Okay, it's a three-membered cyclic ether. Cyclic ether. All right, so the mechanism. Again, there's a lot going on, so try and keep up. Definitely feel free to pause and rewind the video. Okay, make sure when you're drawing it that you orient your starting materials just as I've drawn. I've gotten a lot of practice, so I know how they should go. But they do need to be oriented in just this way. Okay? So, first things first, the alkene is what? Alkene is what? Alkene is a nucleophile. And it actually attacks this second oxygen of the peroxy linkage, the peroxy acid, so the OH part, the oxygen of the OH. In doing so, okay, it kind of does a backside attack and breaks this bond. Okay, so it breaks this bond, and then what can happen is we can have a pseudo type of resonance where these electrons can kick up into the carbonyl. Okay, but at the same time then, concertedly, okay, these electrons can go and grab this hydrogen, and then it's the OH electrons here that come back. Okay, so we took two electrons to form a bond with this oxygen, and then these two electrons from the OH bond come back to form the other bond. Whew. Okay, yes, it's a lot. Feel free to keep practicing. Okay, so again though, here the alkene is doing the attacking. Alkene attacks oxygen. Okay, the electrons are then going to flow around the ring because it kind of does an SN2 right here. It does a backside attack, so it breaks this bond, but then we have some resonance, right, that can take place here. So these lone pairs can kick up into the carbonyl. So I like to think of this as electrons flowing around the ring, around resonance system. Okay. In doing so, this H can then be abstracted. H is abstracted. And then it's these electrons that come back around. Okay? The OH electrons form the other bond with carbon. All right? And yes, this is all one step. All one step. Okay, so this is definitely a concerted mechanism. Concerted. Lots of stuff happening all at once. And I usually tell you guys, only one arrow at a time or one step at a time, but this is a bunch of steps that really do take place all at once. And what's great about this is then we have this nice six-membered transition state. 1, 2, 3, 4, 5, 6. Okay, so this makes it super stable. This whole cyclic, again, six-membered, it mimics a cyclohexane ring, and so it's super stable, this whole cyclic transition state. So that's why it all happens all in one step. Okay, so again, The alkene is a nucleophile. We do like an SN2 and we break this bond. And then we have resonance involved, so we kick the electrons around the resonance. And then these lone pairs on the carbonyl oxygen can go and abstract that H, and then it's the OH electrons that come back around to form our epoxide. But importantly too, we also have that carboxylic acid left. OH. Okay? And if we could kind of label them, right, it's this guy now that has bound with the OH, so we'll kind of label him. And this guy, right, is the one that formed the double bond, so he gets like a dot. If we kind of label how that works. Okay, you see it? Feel free again, the beauty of these videos, we can go back and rewind. Okay? So the most common epoxidizing agent is MCPBA, and that's because it's got really nice solubility properties. It's soluble in lots of things, and it's definitely one of my favorites. And because it's a nice white powder, you just, again, weigh it out and add it to your reaction. I keep saying again. I need to stop saying that word. It's not like we've seen these things before. Okay, so MCPBA looks like this. It's got our peroxy acid, and then part of this benzene ring, this is our R group here. It's got a meta-chloro. Okay, we'll learn about naming benzene rings soon. Sorry, yeah, that's actually OChem too. But this is a meta-chloro peroxy benzoic acid. Okay, again, it's awesome, and this is what I'll often write to mean epoxide formation. Okay, important thing to note about epoxidation is that since its mechanism is concerted, the geometry of the starting material alkene dictates the geometry of the resulting epoxide, right? Because it all happens on the same side of the alkene. So let's say we start with this cis alkene. Okay, it is cis alkene. All right. Again, we throw in some nice white, pretty MCPBA after we weighed it out. Let's practice that mechanism again. Okay, orient your starting materials just as I do. Put that second oxygen right near it, and then have your carbonyl right near your hydrogen. And we can use MCPBA for effect here. Okay, remember the alkene attacks. Okay, in doing so we do like an SN2 and break this bond, and then we have resonance, so we kick around the resonance ring. Okay, and then remember that this oxygen has lone pairs which can come in and attack this hydrogen, and then it's these OH electrons that come back. Okay, awesome. And in doing so we get, right, the epoxide either on top or on bottom of that alkene. Okay, because again, we do react all at once, so it reacts with one face of that alkene. Oops, forgot a methyl group. Reacts with one face of that alkene, and it can do so on top or on bottom. Okay, this will give us a racemic mixture, and importantly, we get a cis alkene, and we get out cis epoxides. Cis epoxides. Okay, conversely, all right, if we use a trans alkene, see what happens. Again, throw in some MCPBA, some nice white crystalline MCPBA, and now it's going to react again. I'll try and draw it bigger this time. OH, O, there we go, nice and big. I'm going to abbreviate our MCPBA though, just abbreviate it, but that's the R group right there. Alright, so again, the alkene is what? Alkene is what? It's a nucleophile, okay? In doing so, we do like an SN2 and break this OO bond, because it's also really weak. And we have resonance involved, so we kick around the resonance ring. And then the lone pairs on the carbonyl can come and abstract this H, and those electrons are what come back around, okay? And importantly, we get a cis, whoa, we started with a trans alkene, so we're going to get a trans epoxide out, okay? Again, we can react with the top or on the bottom, but importantly, again, we started with a trans alkene here, and so we get trans epoxides out. And it is hard to see the cis versus the trans epoxides. Here, hold on, let me finish racemic. But it may be a little bit easier if you kind of draw them with the bonds. Oh, let me just show you. If we draw it like this, if we make the epoxide flat, okay, if we make the epoxide flat, then when we have a trans epoxide, the substitutions coming off are trans. Okay, so here we'll make the epoxide flat, and then we get this guy and this guy. Okay, whereas if we drew the epoxide flat here, both these substitutions, if we brought the epoxide forward, then these would be going back. If we push the epoxide back in the plane of the paper, then these groups would be coming forward. But again, importantly, they would both be coming forward, whereas here, one's coming forward and one's going back. Okay, so these are the, again, the cis epoxides. It's a lot easier when you draw the epoxide flat to see the whole trans stereochemistry involved. Okay, and so again, importantly, sorry I said again, but importantly, this reaction is stereospecific. We've seen this term before when we talked about E2 reactions. Okay, stereospecific. We can't change the mechanism, and whichever diastereomer we go in with, whichever geometry of the alkene we go in with, gives us a particular enantiomer, a particular geometry of our product. Okay, so we go in with a cis alkene, we get a cis epoxide. We go in with a trans alkene, we get a trans epoxide. There's no choice in the matter. Okay, it's always is what happens. Okay, because again, that's because of the mechanism. We can only react with one face of the alkene. We only do so, again, we add across the cis alkene or we add across the trans alkene. So a cis alkene gives us a cis epoxide and the trans alkene gives us the trans epoxide. There's no choice in the matter. Yes, there's a choice of whether or not we can react with the top or the bottom, but in terms of the mechanism and whether or not we form a trans or a cis epoxide, that does not change. Okay, there's no choice in that matter. That's why it's stereospecific. Okay, and I think that makes the videos long enough. We will finish this up on Monday. Okay, I think we have just enough time to introduce cyclopropanation. Okay, cyclopropanation. We're going to make cyclopropanes. Propanes, 3 carbons. Okay, 3-membered ring with carbon, though, with carbon. Okay, not oxygen. So the cyclopropanation of alkenes is most commonly done by use of carbenes. We have not seen these before, but they are super cool and really fun to use because they are uncharged reactive intermediates that have a carbon atom with 2 bonds and 2 non-bonding electrons. So it's 2 bonds and a lone pair. Okay, which is really cool because then they are both nucleophiles and electrophiles in the same molecule. So nucleophile and electrophile. And so they react in a concerted fashion. Okay, so here is our carbene, this guy right here. You can see he's got 2 bonds and a lone pair. So if you actually calculate his formal charge, okay, remember how to calculate formal charge? Remember my super cool formula? Group number minus sticks minus dots. Group number 4 minus 2 sticks minus 2 dots. This guy is actually neutral. Okay, just as it says there, is uncharged. He's neutral. Okay, but what's really cool is that he's got this lone pair, which can be a nucleophile. But you can see he's also only got 3 groups here. He does not have a full octet. And so he's got this empty p orbital, which acts as an electrophile. So we can attack the empty p orbital, but we can attack as in get attacked as in be an electrophile to attack that empty p orbital. But we can also use the lone pairs to do the attacking. So this guy is both a nucleophile and an electrophile at the same time. Super cool. Okay? And in doing so, we form this carbene. We use the carbene to form the cyclopropane. Okay? This 3-membered ring, again, with carbon, not oxygen. Propane. 3. Okay? The common form of cyclopropanation proceeds with haloform reagents, and they look like this. Okay? They've got carbon bound to 3 halides with 1 CH bond. Okay? This CH bond, the H is pretty acidic here, right? Because you can imagine all the halides pulling electron density, and it can easily be deprotonated with hydroxide. And then since halides are stable as X minus, they leave to form the carbene, which is really cool. Okay, I'll show you how this works. We're going to show the carbene formation as well as the cyclopropanation all in one reaction. So don't worry, you get to see it all. Here's our haloform. This is actually bromoform because it's got bromines. And let's throw in some KOH. Okay. But generally, this can be or CHX3, any halide. And this guy we can also use sodium hydroxide. But then our product looks like this. It is a cyclopropane, but it's a little weird because it's got 2 bromines on top. So it's got 2 X's, 2 halides on top. Okay? But here it is right there, that 3-membered ring that we formed. This is a cyclopropane. Alright, how does this work? It's a pretty cool mechanism, okay? Alright, so first up we have to form the carbene, and we do that with the haloform reagent, okay? So like I was saying, all these halogens on here pull electron density away from that carbon and leave that hydrogen pretty acidic. Okay, so this guy is now pretty acidic. And so when we throw in our KOH, our nice good base, KOH, you can go and deprotonate that H. Okay, and we get Br, C, Br. So we haven't formed our carbene yet. Right now we just have a carbon with an anion. Okay, if you calculate his formal charge, group 4 minus 3 sticks minus 2 dots, we have a -1. So we haven't formed it yet. Really quick, it's pretty acidic, therefore it gets deprotonated. Gets deprotonated. Okay, so again, we haven't formed our carbene yet, but have we seen the C- before? We haven't really seen him very much, maybe back when we were talking about resonance. So the C- is not as happy. Not happy. So what can happen though then, is that we know that halides don't mind being on by themselves, being X- or Br-, so they just leave with their electrons. Okay? So that forms then our carbene. Okay? He started with a lone pair, he still has a lone pair, and then he lost 2 electrons from the bromine. Okay, so now he no longer has our minus charge, and now he's only got 6 electrons about him. So again, he's got that empty p orbital. Okay, and like I said, the halides, they don't mind being by themselves. Okay, so the C- may not be happy, but this guy is happy. So that's why he just leaves. Okay, because again, C-, not happy, but we know that halides can be happy by themselves, so they just leave. Alright, so now here's our carbene. Hooray! We have formed our awesome carbene. And so this is when we then bring in our alkene. Here we go. And just like we showed, the carbene has electrons, can be a nucleophile, but it's also an electrophile because it's only got 6 electrons, so it's got an empty p orbital, so it gets attacked as well. Simultaneously, all in one step. So all in one step, we then form our cyclopropane. Sweet. We will pick up here on Monday.